Okay, so welcome. Please just review this information. The way this works is in order to get your credit for PD certificate, basically need to stay on for the whole time and then give me like a day or two. I need to take the webinar report from Zoom and then input the attendance into a different system. So it just takes me a little bit of time. Once I do that, the AD system will send you a survey. It's super quick, super easy, and then you can print your own certificate on your end. So I do not provide certificates for you. You are responsible for printing that on your end through your AD Connect account. And here's a little visual to show you how to do that. And so hang on, we got another person joining. And so welcome. This is a new webinar on constructing explanations and arguing from evidence. Those are two science and engineering practices, and I'll explain a little bit about why we put them together in a minute. My name is Rebecca Gorelli. I am a K-12 science and STEM specialist for ADE, but I'm also a former Next Generation Science Standards instructional coach from Chicago, and I've really been living in three-dimensional instruction since about 2012 when Chicago began adopting those standards. So I'm happy now to be here and helping Arizona implement this new style of standards. So what you're going to see today is really just my understanding of these science and engineering practices as being in the classroom with these standards, but also me as a coach on the side. So here we go. Just a couple housekeeping things. We're not going to get crazy using Jamboard or any interactive tools this time. We're just going to really use the chat, and you don't need to have on your video unless you want to. I'm going to keep mine off just to save bandwidth, and just make sure your chat is turned on to everybody. So here we go. Take a minute, find the chat, and introduce yourself. And what's your current position, job title, and have you had a chance to look at the standards? Are you implementing them? Where are you at? All right, great, welcome. And even if you're still typing, I'm just gonna keep pushing us along because this thing is jam-packed with content. So here we go. Thank you all for being here. I'm so excited to share this new webinar with you. All right, just a couple things. These are the resources that I use to craft this webinar. And so these are just recommended books. These two are really phenomenal on the left here, the blue one and the red one, for really showing students and really engaging them with how to construct these scientific explanations and arguing from evidence. The one on the right here, the K-12 one, is an incredible resource, and it's actually a newer book. And I actually have a free PDF download of this that I will share with you. So that's exciting. All right, I'm just going to invite you to read over the goals really quickly. And so we're just going to start off talking about the instructional shifts just really briefly, and then we are going to spend the rest of the time on these other two goals. And I just want to explain that this webinar is a high-level overview of these two science and engineering practices. And the reason we combined them is because we've noticed there's a lot of confusion in the field about these two practices in particular and how they're the same, how they're different, how do we engage students in both of these. And so we just thought, let's do a high-level overview of both of them together, compare, contrast, and then we're going to build out additional webinars for them like on their own individually. So stay tuned for those because those are coming. All right, let's just take a look at where your comfort level is with the new standards. Are you a 1, a 2, a 3, or a 4? Okay. All right, this is exciting though, because last year when I would do webinars, we had a lot of 1s and 2s. So that means people are kind of moving forward in their learning, which is fantastic. And if you're still at a 2, that's okay. I'm here to help you really think about them and really dive a little bit deeper. So no matter where you're at, I'm so happy you're here. Let's just keep going. If you've been on one of my webinars before, I do use this document a lot because it's my go-to to help educators understand the instructional shifts that come with the new standards. And so I know it looks kind of tiny right now. I'm going to blow it up in just a second, but this is called the New Vision for Science Education. Really a great tool to help understand, like, what are we moving away from, which is on this left side, to where are we moving towards on this right side. And so we're only going to focus on a couple of these today. The ones that really are included in the conversation for the next hour are this one. So take a minute and read that blue box. So we're moving away from rote memorization to this really developing these explanations supported by evidence and reasoning. And then this one. We're moving away from teachers really just posing that one right answer, and we're going to have kids really argue and generate claims and then have to prove that their argument, really makes sense. Down here, we have another one. Instead of worksheets, we are going to make our thinking visible through journaling or notebooks, posters, presentations, and we are going to explain and argue and collaborate. And then this one also coincides with what we're going to talk about today. And we're going to talk about how do you support students in engaging in these practices. And so out of these 4 boxes, jot one idea in the chat about what do you think students may struggle with this sort of putting students in the driver's seat, putting them in the position of the scientists. What might they struggle with? Just drop an idea in the chat. Reasoning, absolutely. That is a struggle. Yeah, and just really making their thinking public through presentations, developing an explanation is tricky. And so if you're not really sure what they're going to struggle with, just know that our students, this is a brand new way of learning, really, where they have to really make their thinking visible and take their thinking public. And so let's just gently move on. And I just want to review how our 3 dimensions are set up in Arizona, which is a little bit different than the NGSS. And so this is a really helpful planning tool. This is called the AZSS snapshot. And it just has our 3 dimensions really laid out here. So up here in the left, we have science and engineering practices. There's 8 of those. Those are what we're going to dive into today. We have cross-cutting concepts, which are the lens through which the students think. And then down here in the yellow box, we have our core ideas of knowing science. So there's 10 of those. Think about content. And on the right, we have 3 core ideas of using science, which is basically how are students engaging with phenomena and making sense of the world around them. And so as a reminder, our 3 dimensions really are combined like this, where these 2 boxes on the bottom actually combine to make the 3rd dimension. And so let's dive into the 1 dimension we're going to spend a lot of time in today, and that's the science and engineering practices. And there are 8 of them. And we're really just going to hone in on constructing explanations, which you can see is yellow, and that's on purpose. The reason it's yellow is because this relates to the science. What scientists do is they construct explanations. Designing solutions in green is what engineers do. And today we're not going into engineer world at all. We're going to just stay on the constructing explanation side of things. So I just wanted to make sure you understood that. And we're going to look at engaging in argument from evidence. Now these do have numbers, but they're just arbitrary numbers as identifiers, like this is number 6, this is number 7. It doesn't indicate a hierarchy or any sequence of any kind. So these are the two we're going to focus on. And so what I don't love about this graphic is that it really looks like this linear fashion, right? But what we know about engaging students in these practices is that a circular visual is much more fitting. And the reason is because if I construct an explanation, well, I bet I probably developed a model first to help me, or maybe I asked a question, or maybe I grabbed some data and analyzed it to help me think about constructing that explanation. Or if I'm over here in the blue section and I engage in argument from evidence, well, in order to have evidence, I must have done something else. I must have engaged the students in planning out caring investigations, or maybe they modeled. And really what we need to understand is that when our standards call out one science and engineering practice, that does not mean that is the only one we engage the students with. We naturally will do 2, 3, or 4 of them within a lesson or within a week, right? In a couple of lessons. And so that's going to be really important for our understanding going forward, is these are not taught in isolation in any way. When we engage in one practice, we naturally will engage in more than one. And so here's a couple of examples of our standards using these 2 science and engineering practices. So take a look, even down at the kindergarten level, these students are asked to explain the causes of phenomena all the way up to high school. And so as a reminder, all of our standards begin, the very first words of our standard are in blue and bolded here. That's the science and engineering practice that goes with the standard. But remember, just because it says construct an explanation, that does not mean that is the only practice I'm going to be engaging my students with. And so we are now going to dive in to the differences and connections between these 2 SEPs. And so let's take a look at this graphic, one of my favorite images out there, about scientific inquiry. And what we need to understand about our new standards is that they really are supposed to be taught in an inquiry-based sort of fashion. And so what I mean by that is, take a look. If we start here in the center with engaging students around phenomena, which is really just events that we can observe in the real world around us, something so simple or something really complex. It's just what's happening around us. And our job is to figure out what is causing that phenomena to happen. So really the phenomena is the effect of what is causing it to happen. So we engage students with a phenomena, and naturally they're going to start to wonder and ask questions about what is happening. So we lead right into asking questions. And after we ask some questions, we go, well, we need to start to figure this out. And so then we can construct some explanations, which incorporates modeling, maybe using some mathematics, and talking about what we think are the causes of that phenomena. From there, we begin to have possible causes of phenomena and begin to investigate them and see if what we're thinking is really what's happening. And we test ideas through experimentation, investigations. And then how do we know what we know? We have to make our thinking visible, take it public, and begin to engage in argument from evidence. And this is really the cycle of this inquiry. And if you're wondering where I got these cards from, I linked them in this presentation, and I will give them to you in the follow-up email. I got them from the Wonder of Science website. So you're going to see me using these cards throughout this whole webinar. And so let's talk about the practices. The science and engineering practices are actually grouped into 3 separate categories. The first category is investigating. Then we have sense making and critiquing. And this is very important for us to understand how these all work. And all of these practices all begin with us engaging students with a phenomena. So we begin with a phenomena. Once we expose the children, maybe it's a video, a demonstration, maybe they're looking at data, something, or they have an experience, we begin to investigate by asking questions, or maybe planning and then carrying out an investigation. And maybe we do some math and computational thinking. We start to look at some stuff. And once we come through the investigating practices, we end up with data. And now once we have data right here, we need to make sense of that data, whether it's qualitative, just what are we seeing, feeling, smelling, hearing, thinking. By using models, we can analyze and interpret data and construct an explanation. So these are the practices that belong in the sense-making category. And so if you look at this sense-making process, we've investigated, we have data, we start to make sense of the data. Now we've constructed some explanations or models through these practices, and now we come down here and we can engage in evaluating the information, thinking of, does this evidence really fit with what we're thinking? And how do we know that? How do we prove that we know that? And that's engaging in argument from evidence. And so now you can see that these are actually broken into 3 categories. We have investigating, sense-making, and critiquing. And here is why I'm explaining this to you. Constructing explanations is actually a sense-making practice because it's going to help us understand how or why a phenomena has occurred. Engaging in argument from evidence is really after you've done some sense-making and you're trying to make your thinking public and say, this is how I know. This is engaging and it belongs in the critiquing. So this is the first reason these 2 practices are not the same. They are different. And so to help us understand the differences, if you haven't really watched Paul Anderson, which is the man right here, he puts on incredible videos. He is the wonder of science. That is his website. He is the guy who made these cards, and he has amazing videos for each of the science and engineering practices. So what we're going to do is we're going to dive into constructing explanations by itself first. We're going to watch the video. We're going to summarize it. We're going to talk about it. Then we'll move on to the other practice. And so give me a minute and we're going to watch the video. I'll pull it up really quickly. And when we come back, I want you to just think about what new learning occurred for you. What were you like, oh my gosh, I didn't know that. Or, oh, I had an aha moment of this video. So just hang on. Let me grab the video. I'll be right back.
Hi, it's Paul Anderson, and in this video I want to dig more deeply into constructing scientific explanations. This has always been a huge part of science, but we want it to be a part of science classrooms as well. We want kids constructing their own explanations for how the world works or why events occur. A really good way to do that is through modeling instruction, where students create their own and construct their own cognitive models or mathematical or computational models. It's basically how the world works. Now remember, this video is part of a series of videos I'm doing on scientific inquiry. I've got a bunch of resources, inquiry cards, and graphic organizers that go along with this. But when I was starting to work on constructing explanations, I had a hard time delineating between an explanation and an argument. What is an explanation? An explanation explains how it works. And what I mean by it is the natural world, versus a science argument, what explains how you know. What was helpful as I was going through this was an article I read by Osborne and Patterson. I'll put a link in the description down below. Essentially, if you're using evidence to construct a claim or to create a claim that's somewhat in doubt, then you're probably doing an argument, and we'll talk about that in a later video. When you're coming up with an explanation, you're determining a cause and a mechanism for an effect that is not in doubt. What does that mean? Well, every explanation is going to have an explanandum, which is essentially what you're trying to explain. So if we look at these 3 questions, why did the dinosaurs die out? Why do we have seasons? And why do things fall? Each of them have an explanandum, which is that thing we're trying to explain. If we move those over to the right, we find that those are the effects, and those are not in doubt. No one doubts that we have seasons or things fall, or if we ignore birds, that dinosaurs die out. What's an explanation going to do? It's going to determine the cause and the mechanism for these effects. So if we look at dinosaurs, for example, you've probably heard a lot of people think there was a massive meteorite impact that threw atmospheric dust into the atmosphere, temperature dropped, and then the dinosaurs died out. And so as we create that explanation, it brings increased understanding to how the world works. And so what explanations do is they really answer those questions of why. Why is the sky blue? Or how do unbalanced forces cause motion? Now, I've found when kids are doing explanations, a graphic organizer with cause, mechanism, and effect is really helpful. So let's say we're looking at the phenomena of antibiotic resistance. So these bacteria in this petri dish are resistant to these 3 antibiotics. So that's going to be the phenomena, so we could put that in the effect. You always put the effect there first. And then we're going to work backwards to determine what's the cause and what's the mechanism. Now, if I were to give you the answer, you've probably heard this before, antibiotic resistance is probably due to overuse and underuse of antibiotics. What's the mechanism? That's going to be natural selection. And so what do we have here? We have a coherent explanation. Now, you might say, I've been doing explanations forever as a science teacher. I was too, but I was probably providing those explanations. Just like I did a second ago, I gave you an explanation. And what we want kids doing with this practice is we want them constructing their own explanations. And this is really hard. You as a teacher have to move from the explainer, the sage on the stage, to more of a guide on the side as the students construct their own models, they construct their own explanations over time. Now, this is based on that constructivist idea of learning, that we all have an understanding of how the world works, and then we have to construct a more coherent understanding. Now, when students are doing this, I've found what's helpful is giving them a cross-cutting concept, cause and effect, that helps them kind of organize their explanations. And also, a fairly recent new pedagogical tool, visual thinking, is helpful as well. We want kids visually showing us their models, what they're thinking. Once that's outside of their brain on a piece of paper or on a whiteboard so we can look at it, then we can start to build explanations over time. If we look at a rubric for what makes a good explanation, it should always have a cause. And then if we're looking at the model that you're trying to explain, you should identify the relevant components of the model, and then how do those connections explain, describe, and predict. These would be the elements of a good explanatory model. Now, if it's an advanced model, you may add numbers to that, mathematically representing some of the elements of that model, or use computational modeling. I've gone into all of this, a video I made on modeling instruction. I'll put a link in the description down below. But if you're just getting started, this is a graphic organizer that I use with students on the left side. I've got also a teacher version of it, so you could look at like what I think are the big elements that you should use as a teacher. But what we essentially want them doing is telling us what they think. And so let's say we're looking at these birds that are dipping. As kids are just getting started constructing these explanatory models, you probably want to give them the question that they're trying to answer. In this case, what causes the birds to keep dipping? Now we want them to create a model. You can think of this as an explanation, explanatory model, or if you want to call it an explanatory hypothesis. It's essentially what they're thinking at this point. Now it's important that since they're going to be drawing a model or a system model, that you curate the important parts that you want in that model. So in this case, if we're looking at this dipping bird, I might tell students that I want the bird included in the model, that cup that they're dipping into, and maybe the surroundings are important as well. And then you want to define the system that you want them to create a model for. Define the boundary in space and time. Lots of times when kids are creating a model, they'll just draw a diagram or a picture, which has no explanation in it at all. And so I would say, I want you to draw the bird in an upright position and then a down position so I can understand what you're thinking. Now we let the kids go. We let them create an explanatory model. This is an example of what that might look like. The student believes that what's causing those birds to dip is gas pressure. Or this would be another explanatory model. Maybe they believe it has to do with density changes within the bird. Or capillary action is a very common kind of a system model when we're looking at an explanation for the bird. But you also want to have a spot where they tell me what they're thinking. What's your explanation? Or what's your cause? I want you to write that out so I understand what you're thinking. Other common explanations, if we're looking at this, might be momentum is causing it to occur, or that we've got a temperature change that causes it to occur. And so now you as a teacher know what all the explanations are in the class. And the next step is to test those models, to test those explanations out. So if we look at where this fits in this whole idea of inquiry, we start with a phenomena. We use questions to develop a lot of explanations, or you could call those models of what we're thinking. But now we're going to systematically test each of those. That's why we do scientific investigations. Some of those models will fall apart. Some of those will have elements that we can kind of combine into a shared classroom model of what we're all thinking. And this is how you can use inquiry in the classroom to construct models as we're all working together. And it also builds that sense of I'm invested if a student is testing out the models that's based on what they actually believe. Let me give you an example of this. I was using this phenomena when I was working with some teachers at American Community School in Amman. So this was a fourth grade classroom. And then their teacher, Jake Owens, what he did is create a driving question board where he put all of their questions up. He then put all of their models up, and then the students are systematically going through and doing investigations to test those explanations to see which ones are wrong and which ones are right. Nice thing about science is there's going to be one reason for why this occurs, and so we can all work together to find that one explanation. So that's constructing scientific explanations. It's what scientists have always done, but we want our students constructing that as well, and I hope that was helpful.
All right, we're going to come on back. Give me a second. And hopefully you found that to be useful. And if you wouldn't mind just sharing kind of one idea, what did you take away from that? What was some new learning that occurred for you in regards to constructing explanations? And we'll take about 30 seconds to drop an idea in the chat box. All right, thanks for sharing ideas. And if you're still writing, that's okay. I'm just going to push us along. And just to remind you, my favorite part about this is when we construct an explanation, it doesn't have to be just a paragraph. It can be a model, an explanatory model where they're just explaining the cause. And we can also incorporate computational thinking. And so let's take a look at what he said. We're just going to kind of summarize it. Here is the rubric that he described in that video. And what I love about it is if I look at this very first one here, identify a cause, automatically connects to a cross-cutting concept. I don't even have to think about it. Down here, I see components of a system. There's another cross-cutting concept that I can connect to. And then down here, computational thinking is a natural connection to another science and engineering practice, and models. If we have components, we need to describe what we're looking for in those models. So really you can see crosscuts and other SEPs are already included here. It doesn't take that much thinking about it. It just happens naturally. And so here is a graphic organizer from Paul. And if you're wondering where I got this, again, it is on his website. He has PDF versions of these graphic organizers for every single science and engineering practice. And he also created Google Drawing versions. So if you're wondering how you can get, kids to actually interact with this, he has them on Google Draw. And so here's how this works. Really, the really important part about constructing explanations is it starts with the effect. And our entire job as educators is to guide the students into figuring out what is causing that phenomena to occur. And so causes really comes next, right? We're trying to brainstorm these causes and think of what's causing that thing to happen. And so again, natural connection to a cross-cutting concept. We have the cause, we try to figure out what's the mechanism that's actually causing it, and then it's going to lead to even more questions, and which can drive us into argumentation later. And I just want to write that in there because you're going to see that come back up in argumentation. And so what does this really mean for in the classroom? How does it relate to our standards? And so if you haven't used this document yet, it's a really helpful tool called the Progression Matrix of Elements, and it spells out what every single grade band should and can do during that grade band to fit this science and engineering practice. And so this is a progression, which means it will increase in sophistication over time. And my other favorite part about this document is that it tells you exactly what this science and engineering practice is about. So if you look at this box, it's really about providing an explanatory account of the world. Constructing explanations is all about explaining. And so let's take a look at 6-8 grade band. These bullet points here are called elements. They can be used as objectives, and I highly recommend using them for planning. If you go, well, what does constructing explanations means for 6th or 8th grade? This is the document that's going to help you figure it out. And your job is to really just choose the element you want the kids to really engage with. So for example, here's one where we look at explanations and variables. That's computational thinking. We have applying reasoning, which is constructing an explanation pretty much. And down here, we can use models or representations to construct an explanation. So again, there's natural connections to other science and engineering practices. And once you get sophisticated at using this document, you can use it for differentiation and look down a grade band or up a grade band. And so if you're wondering where those are, they are on our website under vertical progressions. And so we are going to move on to the next science and engineering practice, which is engaging in argument from evidence. And we're going to go through this same process. We're going to watch the video, we're going to summarize, and we're going to move forward. So hang on one sec, let me grab the video.
Hi, it's Paul Anderson, and in this video I'm going to dig more deeply into argumentation. We support claims with evidence and reasoning. You're probably familiar with CER as a mechanism and how we can get our evidence up on the wall so we can have some kind of an argument. I'll talk more specifically about analyzing and interpreting data and communicating information as two practices that can help us construct a valid argument. Remember, this video is part of a series of videos I'm doing on scientific inquiry, and I'll put a link to that and resources down below. But whenever you're doing arguments, it's important to delineate between an explanation and an argument. An explanation is really explaining how the world works. And lots of times when I'll talk about this in class, I'll refer to this as your explanatory model, how we explain the cause and mechanism of effects over time. When we're doing argumentation, we're really doing the nuts and bolts of how do you know what you know. And so that's gathering evidence to support claims. And a lot of the time, those claims are going to be somewhat in doubt. I did a video on explanation, and I'll put a link to that video down below. But if you're trying to figure out what does an argument look like, you should think about what does a scientist do every day? What does a scientist look like? And you might think a scientist looks like this with a lab coat and discovering something new every day, but they actually look like teachers most of the time. They're spending a lot of time on the email, they're spending a lot of time in lab meetings. Eventually they come up with some ideas and they'll attend one of these. It's a poster symposium, or maybe they're going to give a talk. If we look at this scientific poster, each poster is going to have the following. It's going to have a claim with evidence and reasoning. But we might think it goes in that order, and it doesn't. The first thing you always do is you gather the evidence and see what the evidence shows you. Lots of times you'll have evidence that doesn't end up on the poster because it didn't lead anywhere. I was working in a biofilms lab for a whole summer on bacteria that were just mislabeled in the lab. So a lot of that evidence doesn't show up. But once you've got enough evidence, then you can eventually make a claim with reasoning. Sometimes teachers and students will confuse claim with a hypothesis. It's not what you think. It's what the evidence says. It's what story the evidence tells you. And we want our students doing that. We want the evidence that they're gathering to be up on the wall so other people can see that and we can have a dialogue about what they're thinking. If we look at the sequence of teaching this, it's really important that your kids understand the evidence comes first, and then that reasoning is really, the reasoning is simply connecting your claim logically to the evidence that you have. This is a graphic organizer that I use whenever I'm doing argumentation. It's really showing how you know what you know. I've got a teacher version where it shows you like things that I would include on that. But if I were going to step through, and let's say you're doing argumentation for the first time, the first thing I would do is cover up this, the claim and the reasoning. I would cover up those two boxes. Showing kids that we want to do first is we want to gather that evidence and then see what story that evidence tells. Start with some kind of a simple question. You should probably give them the question to get started, and start with a question where we're going to have some kind of an answer at the end. So how many bones and muscles are in the human hand system? You could look at your hand right now and try to determine how many bones or muscles are in there. Now, they could quickly Google that and they'd learn just arbitrary information, but it wouldn't teach them anything about doing argumentation. The first thing I would have you do when you're ever doing argumentation is underline the terms and define operationally the terms that you're going to use in your argumentation. That'll become really important, especially when you get to reasoning, and students will struggle with reasoning. So maybe we say, as a class, that bones are going to be hard objects inside the body that support. And maybe a muscle is going to be softer objects that move the bones around. And maybe we'll define a system as a group of interacting objects. Once we have that, then you as a teacher let them go. You maybe give them an indication that evidence is what you see, it's what you're sensing, or what you're observing, not necessarily seeing. And that evidence could be qualitative or quantitative, but then you just let them go and they're going to gather that evidence. This is a picture of some elementary teachers doing this argumentation on the hand, trying to figure out what's on the inside. Once they've gathered all that evidence, then they make a claim, which is essentially an answer to the question, and then they're going to come up with reasoning. So you're going to link the claim to the evidence itself. Now, when you're doing that reasoning, you're going to use these because statements from the evidence and tying it to those definitions. This is where those definitions become really important. If we look at some of the posters, these people think there are 29 bones and 16 muscles in the hand, whereas these people think it's 44 and 48, and these people think it's 24 and 19. Now we can get these posters up on the wall, we can look at how they gathered the evidence, and we can start to improve the argumentation that we have. Now, one of the gold standards on doing argumentation is the argument-driven inquiry. They've got a website. They've got some really good peer review sheets that you could go through and look at other people's argumentation. But we then, once we get feedback from other students or the teacher, then we want them to have a chance to gather more evidence and construct a better investigation or a better argumentation over time. Now, if we look at the parts of a rubric on a good argumentation, lots of times you're not doing it in the lab. Lots of times in biology or earth science, you're going to have to go gather evidence that's already been collected. And therefore, the analyzing and interpreting practice is also important. We need to obtain that information. Is this information or is this evidence valid? And then we got to start to see what are the patterns inside data sets and between data sets. What does that mean? Let me give you an example. Let's say we're trying to do the following argumentation. Is Pluto a planet or should it be a dwarf planet? This is actually an argument that's going on in astronomy at this point. And so first thing we would want to do is obviously define those terms of planet and dwarf planet. And then we could start to do research. Where are you going to get the evidence and how are you going to use that evidence to construct an argument? So maybe we're familiar with these different things like Earth, Mars, Mercury, and Pluto, but we've never heard of these other things. And so we want to start looking at patterns in the evidence. What patterns do we see, for example, in their distance from the sun, and their diameter, and the natural satellites, other qualitative information? So we should be digging into the evidence. We should be looking for patterns in the evidence and then see how could we eventually use that to construct a valid argument. So after we've constructed an argument, what do we do next? Then we communicate that information. So the quintessential way to do that is through a lab write-up, but it could also be through a mini poster. Similar to the scientific argumentation that we see in scientists. Or it could be a formal lab write-up, or it could be as simple as kids recording videos of what they learned in the science experiment. And so this is engaging in argumentation. It's claim evidence reasoning. Remember, that's just the product. It's not the process. We should always start with the evidence, and these other practices are helpful there, but I hope that was helpful.
All right, come on back. Hopefully you enjoyed that video. Oops, wrong button. All right, and so just take a minute and drop an idea in the chat as we move on. What did you take away from that? Did you have an aha moment, something new you learned? And I'll give us about 30 seconds before we move on. And so This is becoming one of my most favorite webinars because I know a lot of people do CER in a very regimented way. And that's why I'm here, to help you think about it in a different light. And so we're going to keep working on this idea because that is the confusion in the field of CER. I go claim, evidence, reasoning, when in fact, we can't even make a claim until we actually do some work first. And so we're going to talk about that next. So I'm excited to see some thinking around that. And as a reminder, engaging in argument from evidence automatically can have these other two science and engineering practices embedded with it. They're all connected. And so let's just summarize. We're going to go through this one more time. Really, when you look at his rubric for, good arguments, first, we have to obtain, organize, and then evaluate the information. Which of these things are going to help make my claim and what's not? What should I keep? What should I toss? Patterns, automatic cross-cutting concept included right there. Identifying a claim, reasoning, and communicating. So here is a graphic organizer. This is just one example. I made my own that I'm going to show you a little bit later from my own classroom, but in the nature of sticking with Paul Anderson's idea, here's another one from his website that really starts off with that research question. What are we trying to figure out? And it could, remember at the end of constructing explanations, you had more questions. This could be one of those questions that you start off with. And so my favorite part about this is that we do collect evidence first. We must gather and gather and gather the evidence before we can make a claim. And so you can analyze and interpret data, look at patterns in data, start thinking about things, then make a claim based on what you know so far. And then link it to reasoning, which is telling the story of the data. You would see words like which means, therefore, and I'll show you some sentence starters I actually use with my students when I taught middle school. And then after you do that, you might end up with questions. We always come back to what we still are wondering at the end of everything we do. So we're going to end up with questions again. And really, this is where you get that CER idea, but it really should be ECR when you think about it. And so that's the importance of this webinar. And again, we're going to end up asking questions. This always circles back. And so let's just dive into the matrix again, look at some elements, think about what this practice really means in terms of what students are doing. And again, it's a progression, which means increased sophistication over time. And here, my favorite part is this is different from explaining because we're trying to figure out the best argument based on evidence to explain the phenomena. And so let's look at 6.8. Reminder, these are called elements. They can be used as objectives or, as I mentioned, differentiation once you get used to them. And really, if you look, it does include writing an argument, but it doesn't have to be the classic CER, here's your graphic organizer, get it done sort of thing. That's just one way of doing it. And I'm going to show you from my classroom, I did it a completely different way. And so it can be oral, it can be written. You can bring up your evidence. We can talk about whether we support it or we're going to toss it out, we're going to refute it. And we can respectfully critique each other's work in our collaborative environment. And really, these are the two science and engineering practices that connect to this. And again, those are on our website. And so here is one of my favorite articles of all time. I did provide this in the email I sent out ahead of time, but I also will give it to you afterwards as well. Inside this article, there is this beautiful scientific practices continuum tool here. And we're going to look at constructing explanations. So this is kind of like a rubric, but more of a performance rubric. Like, what should we expect the students to do? And we're going to look at engaging in argument from evidence side by side. And so here's constructing explanations. And if we're at the exemplary level, really, explanations is about explaining how or why a phenomena occurs. That's it. That's the point of the explanation. How or why is something happening? Because it's a sense-making practice. Down here, engaging in argument is totally different. Look at the exemplary model here. This is student-driven argumentation, engaging in discourse. This is a process. This cannot be done in one day where we say, okay, kids, today we're going to do a CER. That is not the intention of this practice. And I'm not saying that's bad. Sure, we need to practice with students, and that's great, but it is a process where they gather evidence, collect lots, gather, then they make a claim and reason through it. Then they make it public. Kids can provide feedback. They can change their idea and redo it all over again. This is a critiquing practice and why these two are not the same. And so let's dive into the final piece where we dive into CER. And I'm gonna go through this a little quickly so that you can see the video. So here, I'm sure some of you are looking at this going, I've seen that before, because this is really a popular graphic that you'll see in a lot of, not necessarily older, but when NGSS first came out and those two books I showed you about constructing explanations, this is in there. And this has caused some confusion in the field for two main reasons, including myself. And so let's break this down. I'm sure a lot of you have seen this: claim plus evidence plus reasoning equals an explanation. Well, knowing what you now know about explanations, this doesn't exactly fit. And the reason, there's two big things here. First of all, another big misconception in the field is that this is similar to how ELA does claims, evidence, reasoning. They do the claim with your justification, but it is different than ELA. The claim is not an opinion. I'm not just asking you to look at something and tell me what you think. That is not what we're doing here. A claim is after you have investigated, designed, modeled, asked questions, looked at data. Now that you've done those things, now you can make a claim because you've done some work already. That is the first thing. The second thing is that this is called an explanation when it really is not the science and engineering practice of constructing an explanation. It is actually, this CER process is arguing from evidence. And if you're wondering how I know this, it is literally spelled out in page 212 in this book. And so I hope that doesn't make anybody sad or mad or anything, but there is differences and it's really confusing in the field, which is why we are doing this presentation now, is because we've heard this and we wanted to sort of clarify. And so let's just walk through this. And if you didn't know, CER actually has an additional R called the rebuttal. So I'm going to walk through that kind of quickly because that's not the focus. But really, a claim just answers the question. Really, that's it. Evidence, any scientific data that supports that claim. The reasoning, the hardest part is to tell the story of why that piece of evidence supports the claim. This is where we'll see words like which means, this is therefore, so I know this, which means this. You're going to see those words in a second when I show you some sentence starters. And then the rebuttal comes from, okay, now that you've gotten really great and sophisticated at CER, what about the counter argument? What about the other side? And doing a rebuttal really talks about the alternative explanation. And basically you do a CER for the opposite side. And so we're not going to get into rebuttal. And here's why. In these books, which are written by the same author, they have a lot of the same graphic organizers, like this image here, talks about the sophistication and the variation of doing CER over time. If I'm in a kindergarten classroom, I may just think about claim and evidence. We think this, we think this is the cause because this. And then as kids get older and more sophisticated, then we pile on. So instead of just one piece of evidence here, we ask for a few pieces of evidence. And this is called setting criteria, telling the students what the expectation is so they can perform to the expectation. And so at 6-8, which is the video I'm going to show you from my classroom, I taught middle school, is multiple pieces of evidence. You're going to watch me define those pieces of evidence with my students, and I have the expectation of reasoning as well. I didn't even get to rebuttal any time I taught middle school, except for one time when I taught 8th grade and I had a group of kids who could do it. And so today we're going to focus on this. How do we get into this CER mentality? And what I'm going to show you is from my own classroom. This is, I called it a clever claims evidence reasoning instead of a CER, but I used it as a summative CER. Not just today we're going to look at this, give me a CER, put it on paper. It was a whole unit where they collected evidence over time. They did models, investigate, they presented their ideas, they critiqued each other, and then they made a final written product. So here's the story. This was a erosion and deposition, like a weathering unit on earth processes. And there was this town, a fake town called Boomtown. It had rapidly increasing population, not enough housing. So the students had to solve the problem by figuring out where the town should build new apartments and houses and then recommend it to the city council. So there were 3 places they could choose from: the hill, there was a marsh, and a cliff. And so what I'm going to show you is how, after doing all of this investigations, I asked them to present their final idea. So that's what you're going to watch here in just a second. So hang on. Let me grab the video. Too many videos. Okay. And please forgive the wobbly video. I had an academic coach scheduled, but they had to cancel, and so I had to call my husband quickly to come help. So today, you guys are going to do your first clever scientific explanation. Here we go. Okay. We have a question. The question is, where should Boomtown build its new apartments and houses? Should it be at the seaside cliff, the Delta Marsh, or the Green Hill? So to write a clever scientific explanation, there are 3 parts. CL stands for what? Claim. So our claim. We have a question, and the claim is simply your answer or response to this question. So how many of you have already decided on which place you would like to build? How many of you picked the cliff? Anyone pick the hill? Did anybody pick the marsh? Okay, so we have already made our claim. Okay, our claim is our answer to this question. EV stands for what? Evidence. Evidence. This is all the scientific data and information that supports your claim. Why did you pick that place? There has to be some reasons, right? So, when we do this writing today, I'm going to ask you to provide at least 3 really good reasons, pieces of evidence to support your decision. On top of that, I'm going to ask you to provide 1 trade-off. So remember, a trade-off is exchanging one thing for another. So if I have all these good things about my location, I have to explain at least 1 negative aspect of that location. Okay? After we do this, we will move on to the R. And what does that stand for? Reasoning. So reasoning. This is the hard part. This is where we need to explain, how does that information from the piece of evidence support the claim? Okay, and I'm going to help you with this today. When you start your work, I'm going to walk around and I'm going to just ask you questions to help you think through your reasons. Cool? All right, so here's how we're going to do this. Where should we get evidence from? You guys have been working and working and working for, I don't know, 8 weeks on this. Any information from your notebook and from the text is where we're going to go. I want you to think of all the things you have done. You can use the street map, the topographical map. You can use anything from when we did the river model, the hill model with the rain, or the cliff model with the waves. Any of that data is acceptable. You can also use information from when you weighed the advantages and disadvantages, and the geologist's report when you collected all the information about the earth, right? Like the soil and the risk of flooding. You can use any of that. You can use any of the ideas from when you made your group presentations. All of that is part of your evidence. Then, if you remember, we presented our findings and did a gallery walk. You can use any of this information. Sound good? Do we have a lot of evidence to pull from? Yes, you do. So how are you going to collect this evidence? Well, I made you an evidence collector. In this column, okay, you are going to at least provide 3 pieces of evidence, then work on the reasoning. So why is that piece of evidence important? And then you're going to tell me where you found that evidence. What source? Was it a map? Observations? A data table? Was it in your notebook? Was it in the text? Then, I gave you a box for trade-off and the solution. Remember, the engineers offered solutions. We have now learned that we can solve a problem at one of these places if we need to. The yellow box, down here. I'm requiring you to give me at least 3. If you find a 4th or a 5th piece of evidence, that is the bonus box. That is going above and beyond. And you can get extra points. Cool? Any questions so far? All right, so here's your task. You're going to work for the next 15, 20 minutes with your partner, finding the evidence, okay? Maybe 10, 15 minutes. Are you ready to begin?
Yes.
All right, dive in, collect all.
Okay, and so that was just sort of how I set it up with the students. And then I want to fast forward so they work. And then hang on, they keep working. And then you know how it goes. Some kids are ready to move on to the next. You can see them working in their notebooks, filling in the evidence collector. There it is. And then hang on, let's keep going. Oh, where does it come in? Hold on, sorry. There it is. So once the students were ready to move on and I needed to help them with the reasoning, which is the really hard part. Give me a sec, sorry. I had these bookmarked. They're not there. All right, I'm gonna show you what we did next for reasoning.
Evidence. So what are we gonna do with all of this evidence? We're gonna put it all together in a beautiful piece of writing. So what I have for you on the back of your evidence collector, I'd like you to just turn that paper over, please. For each section of this scientific explanation, I provided you some sentence starters. So, I gave you a sentence starter for your claim, for evidence 1, reasoning 1, evidence number 2, etc., etc. What you're going to be doing is writing everything you have just put in your evidence collector in a graphic organizer that looks like this. So it starts with your question. After we have a question, we answer it with a claim. After the claim comes our first piece of evidence and the reason why that evidence supports the claim. Does that make sense? So if you follow these arrows, you will be successful. Just go in order and I will walk around and help you piece this together. So here's how this works. You're going to get this paper, okay?
All right, so that is where we're going to stop for now. Hopefully you kind of saw how I worked this out with the students. And to just clarify, really they had done all of this work over the course, and this was a summative sort of culminating CER. They had done map work. They really spent time investigating, developing models, constructing explanations of the 3 locations using materials. These are called investigative phenomena, smaller phenomena that's going to help us figure out the whole thing. And they collected even more. They already picked a location, weighed the advantages and disadvantages. Then they got a little more data. Then they went public with their thinking. So now they're in critiquing mode. And then they took their thinking public. And then students walked around and provided feedback and really critiqued. And then once they went through all of this,
Then they made a final claim and collected evidence. This is what the evidence collector looked like. Here are all the sentence starters. And yes, I will provide this for you so you can see kind of how I thought through it. And I just basically had them highlight one sentence starter for every section. Kids need these scaffolds. They absolutely do. And then I built this to really just show them how it goes. It's super easy. And then I had a very basic scoring guide that I use for every time I ask them to do basically evidence. And so really, how do you make and support students so that they're successful? Did you see how many opportunities they had to make sense before they made the claim? That is really important. Also, setting criteria. How many pieces of evidence? Do you want 3 pieces? Where should it come from? How about a trade-off? What about a risk or a benefit? Think about what they're going to write and tell them. Tell them what they need to do, and they will be successful. And then obviously sentence starters and supports. Get them in their science notebook. Provide talk moves. How do they talk to each other? All of those things are important. And so we are done. It is 5 o'clock. And how this works is I will take attendance probably tomorrow morning. It will send you a survey to your email. Once you fill it out, you can print your certificate. And here is the document I will be sending to you. So right here, if you look where my cursor is, I gave you my whole Google Drive folder of my CER work that you just saw in that video, including the video and including a video of my students' notebooks from that unit. So if you want to see how I set up notebooks to make them successful, you can dive in and check that out too. I also gave you this other sort of practice one I found online. It's not my favorite, but at least it's something to get you started. And so that will also come. And just to remind you, we are working on our new website. We have revamped all of our resources. So make sure you go there. And thank you for being here. That is all. So thanks for being here. And I'm happy to stay on if you have any questions. I'm happy to do that.
Rebecca, this is Letitia Finley. How are you?
Hi, good. How are you?